Future-proofing global supply chains depends on strengthening maritime choke points, which are vital to the resilience of maritime trade. This 2024 statement from the United Nations Conference on Trade and Development captures a central reality. Although more than 80% of global goods move by sea, much of that traffic passes through a small number of narrow canals and straits. These choke points enable efficient trade, but they also concentrate strategic vulnerability within the marine transportation system. In recent years, that vulnerability has become increasingly visible. Drought has reduced capacity at the Panama Canal, while insecurity along the Suez route has forced vessels to reroute around Africa, adding time, distance, and cost to global trade. In response, the Federal Maritime Commission opened a 2025 investigation into choke point vulnerabilities, citing congestion, climate stress, and geopolitical competition. At the same time, U.S. liquefied natural gas exports have grown rapidly, making the United States one of the world's leading LNG suppliers and a central player in global energy security. I'm Lisa Woodman with the United States Coast Guard. I currently work in port, vessel, and waterways safety and security in Southeast Texas. In my thesis, From Canals to Arctic Fronts, Advancing Marine Transportation System Resilience through Network Science Modeling of Choke Points, I use U.S. LNG exports to model a maritime trade network and examine how choke point disruptions and potential expansions reshape global supply chains. The study focused on 3 research questions. Which maritime choke points matter most to U.S. trade? Which indicators best measure system stress and resilience? And which routing or infrastructure investments most effectively strengthen trade resilience? To answer these questions, I developed a geospatial maritime network model in ArcGIS Pro, mapping U.S. LNG export flows from 2016 to 2024 through 9 global choke points to 41 importing countries. The method followed 5 steps. A routable global shipping network was built. Trade volumes were then integrated to weight these routes. Standardized metrics were applied. The network was stress tested across 6 disruption and expansion scenarios. And finally, results were compared by holding trade volumes constant while changing only the network structure. This isolates how geography and infrastructure shape system behavior. The results show that choke point dependence is measurable and unevenly distributed based on geography. For U.S. LNG exports, a Panama Canal closure produced the broadest global impact. A Suez disruption created less severe but more regional strain, and a dual closure had the largest effect, though only slightly greater than the Panama alone. One unexpected finding was the importance of the Strait of Gibraltar, which emerged as the most structurally critical node for sustaining trade system connectivity. Across all disruptions, trade continuity was preserved by rerouting through longer Cape routes, but at higher cost, longer transit times, and greater fleet requirements. The consistent insight is clear. Routing availability governs resilience. The expansion scenarios show that resilience can be designed, but not all investments offer equal value. The most beneficial option was a Pacific-facing Alaskan export terminal, which shortened voyages, reduced choke point exposure, and lowered delivery costs by $1.5 to $3 billion annually. Arctic routes currently offer no benefit for U.S. Gulf origin LNG exports, but these routes, specifically the Northern Sea route, is beneficial to competitors like Russia and China. A trans-isthmus pipeline across Panama could provide a bypass during drought conditions, depending on capacity and cost. Together, these results show how targeted infrastructure choices reshape trade resilience. To translate analysis into action, the thesis then proposes a maritime resilience dashboard that integrates routing maps, choke point metrics, and scenario results to enable planners to visualize vulnerabilities, compare options, and assess redundancy over time. Although demonstrated through LNG, the framework scales across commodities and modes. As competition, climate stress, and conflict increasingly intersect at sea, access to maritime choke points will shape U.S. energy exports and trade resilience. By modeling these trade flows as a system, measuring choke point vulnerability, and evaluating deliberate infrastructure choices. This project shows how the marine transportation system can be better prepared for disruption, and how targeted investment can strengthen U.S. resilience in the decades ahead.